Okay, good morning. Let's start. Okay, so what I'm going to do is I'm going to finish the example from previous lecture, okay? And then we'll get on to the new topic, which is arc lengths and line integrals. So in previous lecture, we talked about the vector function, basically parametric equation. And then from there, it leads to, if we have a parametric equation or vector function, so a couple very important vectors that you can derive. One is called the tangent vector. Which is simply the derivative of the position vector or the vector function. And the other one is a unit tangent vector. And that's simply just normalized version of this tangent vector. Okay. And then for the same curve, and then it's basically there's a normal vector. So normal vector is derivative of the unit tangent vector over dt. So the derivative unit tangent vector doesn't necessarily give a unit vector, so it's still normal. So we need a usually we need a unit normal vector, and that can be obtained by normalizing the normal vector. Okay. So, and finally you can get a so-called binormal vector, which is the product between t and n and here. So this is essentially what we learned from previous lecture. Okay. The three vectors you can derive from a vector function. More important is this unit vector set here. Okay, this is what really interested a lot of time in the application. You will use this for tracking a mobile frame, basically attached to the curve. Okay. Okay. So let's just finish the example from previous lecture. Finding all these three basically unit vector. Okay. So giving you a vector function t squared 3t phi. Okay. So we'll try to find the three unit tangent vector t hat, n hat, and b hat. If you know Maple, you use a symbolic actually toolbox. If you calculate symbolically using a software, it's actually quite straightforward. But of course, when you do assignments or exams, you have to calculate by hand, right? So let's just rewrite whatever we have done in the previous lecture. Okay. Okay, so that's your tangent vector. Unit tangent vector is just to normalize this. Okay, so that's your unit tangent vector. In order to get the unit normal vector, so we have to calculate, it's dt here, right? We have to calculate the derivative of the unit tangent vector first. Okay, so that's basically where we left off in the previous lecture. So calculating this unit tangent vector, which is basically calculating calculating this whole chunk right here, right? You calculate derivative for this unit vector. So meaning you calculate the derivative for each one of the components added here. Okay. So let's see we calculate this one here. First 2t over 4t squared plus 9. Okay, so calculate the first component. And we mentioned that in this case you can use a quotient rule. Some students said I prefer to use product rule. Is that be alright? Of course. So if you prefer to use product rule, basically you consider this whole thing as one function, or you consider this as a 2t times 4t squared plus 9 to the power 1 half, and then you can use product rule, right? So which is sorry, there's 1/3 negative here, right? You can use product rule, that's okay. Okay, but if you choose to use quotient rule, okay, as we said, basically u over v's derivative equal to v squared u prime v minus v prime u. So you can easily get by substituting into this formula right here, and you will be able to get essentially at the end, okay, v squared 4t squared plus 9 u prime is 2 times v 4t squared plus 9 minus v prime times u. So u is 2t. V prime, this is the bottom is v at here. So that's 1 half 4t squared plus 9, and then negative 1 half times inside the derivative, which times at. So that'll be the v prime at here. Okay. So this is what we end up at the end. Previously, we end up at this location. Okay. You don't actually stop here. You need to basically to clean it up before you move ahead and then do the normalization of this vector here. So clean this up. Let's see how we can clean it up here, right? So this is a 4t squared plus 9 to the power negative 1 half. Maybe clean up a few things. So this is essentially 2 times 4t squared plus 9. This is 1 half. Okay, and then 2t times 2 and 2 cancel each other. Okay, t times t at squared over this is 4t squared plus 9. Okay, 1 half, right? So if you write it down one more step right here, basically. Okay, so now you can see this term here, combine the term at the top over here. So when you time this and this, that 1 half, right, becomes 1. So that's just 2 times 4t squared plus 9 minus at squared divided by this term times this term. So that's 1 plus 1 half. So that's become 4t squared plus 9, 3 over 2. So that's the simplification. Then the top one here can be simplified a little more. 2 times 4t squared minus at squared cancel each other. So just end up with 18, right? Okay, so that will be the derivative of the first term at here. Okay, first term. Is that good? So from my past experience, a lot of students making mistakes somewhere over here. So basically how you can apply the quotient rule, and some student making mistake when doing this simplification at here. Okay. Yeah. So you can use a similar method now. So to calculate what is the derivative of the second term. Okay. Is there any question here? So through this course, usually you will brush up on your derivative skills. Okay. So second term, you can use a very similar approach as we did, just like this. So we really want you to try it. And often in time, if you have any doubts, the best way is to try it again yourself. So I'm gonna get and we're gonna get this one as a result for the second derivative, or the term of the second derivative term. Okay, so that's this and this. So then now you can get the derivative. Any questions? Yeah. So now you can get the derivative for the unit tangent vector, which is, there's a common term, which is 1 over 4t squared plus 9, 3 over 2, right? So both term has this common term. But inside here is 18, negative 12t, and 0. That's your derivative, right? Yeah, for the unit tangent vector. So this is not a unit vector. And we normalize this vector. We normalize this vector to get the unit normal vector. Okay. So now, before we normalize, of course, we need to calculate the length of this vector. Okay. Yeah, the length of the vector. So the length of the vector, if you do the calculation at here, you're going to get basically this is a common term. So when you calculate the length of vector with a common term, actually won't change. It still stays as it is. So that's basically 4t squared plus 9, still going to be here. Okay. It's called because it's common. Okay. And then essentially 18 squared plus 12t squared in the under the square root. Okay. Yeah. And here you can actually simplify this, and then you end up with a 6 over 4t squared plus 9, 3 over 2, square root, okay, 4t squared plus 9. So now you can see here now. So this term and then the bottom here, they can cancel partially, okay, not completely. They can be canceled partially at here. So that could be simplified a little bit further, which becomes 6 over 4t squared plus 9. Okay. Or you don't have to do this. This is optional. Okay, you don't have to do this part, this simplification here. The reason is because you're gonna use this term divided by its length, right? It's probably better keep it that way, because in the dt hat over dt you have this one in here. In the norm, in the length of this is also have this term, so they will cancel each other out, right? Yeah. So that basically you get your n hat now. Okay. And you get your n hat, which is 1 over 4t squared plus 9. Okay. Inside the vector here is a 3 I hat minus 2t j hat. Okay. Well, you don't need I guess I don't need I hat. If I use an angle bracket, I need I hat j hat. Okay, and then you can add a 0 here just in case. Okay, so that's your n hat. When you use this divided by its length, okay, and you get this. So just be extra careful with it here, right? So finally, you get your t hat, you get your n hat, and finally you can calculate this t hat cross n hat. Okay. Actually, I don't really have an answer here for the b hat. Maybe for your own exercise at here, what will be the b hat? Okay, that's a cross product. Okay, yeah. But you can imagine it's a little bit complicated because you have these terms at here. But you can always keep this as a constant term, as like a scale, right? So that term can be outside everything, and then you just had to calculate this. Okay? Well, actually, it's different. This is 3 over 2. This is 1 over 2. Okay. Anyway, you can try it yourself. Okay. I do have a Maple file. Actually, I'll post it on the Blackboard on the Connect. I use basically the software to calculate what the t hat, n hat, and b hat is. Okay. So you can verify yours with the software solution. Okay. Yeah. So it's very standard process in terms of calculating the unit tangent, unit normal, and a binormal vector. Okay. So really nothing too sophisticated here. I do have one more example, but this is very much related to one assignment question. So Let me just quickly go over this example right here, because I noticed a lot of people haven't really come across such kind of example before. Giving a vector function, which is this one in here, so that's a vector function, all right? This is actually a so-called a roller coaster function. Okay? So if you plot it out, and if you plot it out, it'll look like this kind of shape. Okay. So if you go to any amusement park, the curvatures of a roller coaster are actually mathematically designed, not arbitrarily designed. So part of that curve probably is part of the curve can be described by this vector function right here. Okay. Yeah. So if you look at this vector function, okay, this is your x of t, this is your y of t, and this is your z of t, right? So that only describes the trajectory, right? So it's the trajectory of the curve. And the trajectory x of t, you look at this, x of t is actually a function of theta first. Or same thing for y, it's a function of theta first. And then z is a function of theta, right? And then theta is a function of the time, okay, of the time. So that's a sort of a so-called, basically, often in time, implicit, right, type of function. It's embedded. So now the question here is, can you calculate the velocity, okay, the velocity of the roller coaster? So that's really what matters, right? You know, what makes people feel more comfortable or generating more adrenalines? You know, that's the velocity part. So if it's a fastly changing velocity, okay, then that's where you feel this thrill, right? So then how do I calculate the velocity in it, right? So this formula, of course, is a derivative of the position vector giving the velocity. In this case here, so what we need to do is basically we just need to calculate three derivatives. Okay. Yeah. Okay. So let's calculate the derivative here. Let's calculate each one of them. Okay. So as we mentioned, you look at the x. X is a function of theta. Then theta is a function of t. So theta is basically how the angle changes, right? So in this case, the question didn't tell you how the angle changes. It's like basically the moving profile here. So what we can do is we can just treat it as a sort of a symbolic type of situation. So you essentially you do a chain rule at here. Okay. So dx over d theta and then d theta over dt. So dx over d theta, it's like a d sine of theta at here. So that's basically cosine theta, right? It's basically cosine theta. And d theta over dt, so d theta over dt, the question didn't tell us what the theta function is. So all we can do is we just keep this theta, d theta over dt at here. In general, if it's a time function, remember we use this Newton's notation, we can use a theta dot. So that essentially is the dx over dt. And you can try dy over dt similarly. So this is your y of t at here. Okay. So dy over d theta over dt. It's a sine 2 theta. So it's 2 times cosine 2 theta. And then times theta dot. Okay. Yeah. So finally you can use dz over d theta dt. So that's negative sine theta and then theta dot. So that's it. That's basically you put all the three terms, okay, back over here. Okay, and that's your velocity. Okay, that's velocity. If the question is given the theta function at here, then you can actually calculate what theta dot, right? Okay, but otherwise we just keep the theta dot at here. Okay, yeah, as a general expression for the velocity of this roller coaster function. Okay. Okay, so there's one additional section in the lecture which describes so-called the curvature. I encourage you to read it. Okay, it's not part of the, not going to be tested or exercised. Okay. Yeah. Any questions regarding the vector functions? Okay, or basically derivative integrals on vector function? Yeah. Okay. Good. Okay, so let's continue here. Okay, let's talk about the new topic now. Arc length and then scalar line integral. Okay. This is most probably this is going to be the lecture that's going to be covered by the midterm. Okay, and maybe there will be one question on the partial derivative, but this is a very important part of the lecture, so there will be a question on this portion, okay, on arc length or scalar line integral. Okay, yeah. So let's look at the arc length first. So arc length. Maybe just a quick review first. So in 2D, okay, in two-dimensional case, suppose that you have a function y equal to f of x. So the question here is basically, how do I calculate the arc length, for example, from here to here? Right? So basically, how long is this portion of the curve? Right? That's basically the concept of arc length. So in order to do this, you probably actually learn this. I think you should be in 173. Okay, so to take care of this, so what typical approach is, you do like this. So it started from this location and here. So suppose this is A location, and then stop at a B location. Okay. So then what you look at here is you can draw a triangle at here. Okay, you can draw a triangle. Okay. So here, let's say representing delta x change, then this side here represent the delta y change. Right, so from A to B, there's x change and there's y value change. So that's delta x and delta y. Okay. So the hypotenuse at here can be noted as a delta L, right? So basically, the delta L, you can use it, okay, as an approximation for the arc length, right? For this arc length here. Okay. So for example, now we can see, okay, so delta L equal to, using the Pythagorean rules here, so delta x squared plus delta y squared. Okay. And now, okay, I'm going to do a little bit further simplifications, right? So that's your delta L. So you learned in the calculus, basically for scalar function, this triangle right here, this one here, basically representing what can be represented, it's the slope, right? It's the slope at this location right here. So we draw the triangle here tangent to this point, so that's the slope. And the slope is basically the derivative, can be represented using the derivative of this function here. So the delta y, okay, can be approximately to be basically the slope times the delta x. Actually, in this case, not approximate, it's equal. Okay, yeah. So derivative represents a slope, tangent theta, and then times the delta x, right, give you the delta y. So I can replace this delta y with with this expression, right? This expression. Okay. So a little bit of simplification. We've got a common term delta x out of here. So take out the delta x, and the delta x will come out of the square root now. But inside the square root, you have and you have this term. Okay? You have this term. So basically, your delta L, which is this length of the hypotenuse here, equal to square root 1 plus the derivative square, and then times times the delta x out of here. Okay. Yeah. Okay. So now we do a little bit approximation. So this is a very general. It's delta x, delta y. So now I say, okay, if delta x goes to 0, so basically as the b is approaching to a infinitely, right? As b is approaching a to infinitely, then this delta L will become a dl, right? So that's the limitation. That's the derivative idea. So the dl will equal to basically square root 1 plus let's see, if I write df over dx out of here, square, okay, times dx. Okay, so that's when it's approaching infinitely here. That's your dl. Okay, then if I integrate both sides, okay, then we get this so-called arc length now. So if we integrate both sides here, so we get essentially a certain arc length equal to, so from a to b, okay, 1 plus df over dx square times dx. Right. So that's the arc length. You know, if you recall, this is how you learned in 173 possibly to calculate arc lengths for 2D curves. Okay, 2D curves. Okay, is that good? Okay. So now let's extend this, okay, to 3D now. So let's say we have a curve C in 3D, and we're going to do is we're going to see here is A location, and here is the B location. So we have a position at A, and we have a position at the B, right? So naturally, you can create a vector from A to B. So in 3D space, same question. So how long is this arc length, or how far does it travel along the curve C? The displacement from A to B. So it's like the S equal to what? The displacement. Okay? Same kind of question. Okay. Okay. So let's see how we can derive a formula. Okay. It's going to be a little bit different, but it's actually, you will see it covers the case for 2D. Okay. So let's see, how do I derive this? So I'll do a very similar kind of approximation, right? So we start from a relatively big distance, and then we'll shrink to smaller ones. Okay. So let's see, if I'm going to use the vector AB, okay, so let's call this delta R. Okay. If I'm going to use the delta R as a representation of this displacement, right? That's the representation. So the S, or let's call it delta S right here, is approximately the delta R. So the length of delta R. So approximately. And then you can look at this graph, and that tells you immediately. So what's delta R? Delta R is what? The vector R at B location, subtract the vector R at the A location, right? Okay. Yeah. Okay. So what we want is I should actually write the order should change a little bit. I should write this first and then write this one here. But actually it doesn't matter. Okay. So let's look at this guy here. Okay, let's look at this one. This is a delta R right here. Maybe let me write down again. So this is delta R. So now I'm gonna write the delta R. This is the value, the length of delta R, right? The length of delta R. if you recall from previous lecture, to represent the length of a vector, I can use an alternative expression, which is what? Using the dot product. So if you use the vector dot itself, yes?
In the delta are the to the b minus a. They're going to be b.
Here?
Right below that. Versus r a minus r b. R b minus r a.
Oh yeah, you're right. Sorry. Yeah. Well, if I put a absolute sign here, actually it doesn't matter now, right? Yeah. Yeah. Okay. So the length of vector can be represented as a square root of its dot product with itself. Okay. So that basically the length of the arc length can be represented approximated using this formula here. Okay. And then I'll have one more manipulation. So no change. Okay, just manipulate it. So what we do is we're gonna divide the delta t at here and divide delta t at here. So divide each term by delta t. Okay, right? Divide by each term by delta t. But if I divide each term by delta t, so I had to time the delta t, right, in order to keep the same expression. So basically you time delta t squared here, right, to keep everything still the same thing. You time delta t squared, so the delta t square root of delta t equal to basically delta t, so you can move the delta t outside the square root. Okay, yeah. So that's one step of manipulation in here. That's it. Okay. So now you look at this expression. So this is approximately the length, arc length, expressed using this formula. Why is it approximate? Because what? Because it's a relatively big delta t, right? So if my delta t actually goes to 0, okay, goes to a very, very small number, then this arc length, instead of a delta, it'll become straight d now, right, infinitesimal. And instead of approximate equal, so as it's shrinking and shrinking so small, that's not going to be approximate anymore. It'll be just a straight equal now. So equal to, every delta will become straight d. Okay. It'll become this now. Okay. So now the arc length, infinitesimal arc length, right? This is infinitesimal arc length is equal to this square root times dt. That's infinitesimal. What we're looking for is basically it's an arc length from a certain location to another location. So let's say, for example, at this location it's t equal to t1. At this location is t equal to t2. Okay, so at t equal to t1 moment at A, t equal to t2 moment at B. Now we can integrate both sides. We can integrate both sides now. Okay. Then that'll give us the integration of d anything, give us back that something, the s. And then this equal to integral of this one. This is in terms of t. So we can see this is from, let's say, from t1 to t2. And then square root, okay, dr over dt, dr over dt times dt. That's it. See, this is basically a formula for arc length. So this is arc length from t equal to t1 to t equal to t2. Or how far it travels along the curve. An alternative expression, you can always write this expression. You can always stick to this one. That's fine, okay? But you can always write it just slightly as I was going to show you it here. So if your r of t is given as y of t, z of t, x of t, z of t. So if we substitute r at here, okay, substitute into this one, so we'll be able to see that this s, okay, t1 to t2. Okay, so dr over dt is dx over dt, dy over dt, dz over dt. And then you dot product. So then basically you get dx over dt squared plus dy over dt squared plus dz over dt squared times dt. So that's an alternative expression for arc lengths. Right. So either formula will work, and often in time I actually prefer to choose the first one here. Okay. But either one will work. Okay. Good. Now, I want you to verify this. Okay. Basically, remember this is I said this is a 3D curve, which include the case of 2D curve, right? So how is this one will include the case for the 2D, which is which one? Which is this guy here, right? Which is this guy. Okay. Yeah. So let's take a look at this scenario right here, right? So let's say if this curve, okay, so 3D. So for 2D, basically means what? The z component is actually is a 0, right? So z over t is always 0. Okay. Then this formula will become t1 to t2 root dx over dt square plus dy over dt squared and then dt. Okay? Yeah. Does that make sense? Okay. So this one should be the same. Okay, it's supposed to be the same as the formula we just derived for the 2D as this one here. So if I write it just slightly at here, okay. If I write down the other one at here, which is from A to B, 1 plus df over dx square and dx. So if you look at these two at here, right? Look at these two. Okay, how are they going to be the same thing? They don't look like the same, right? At least by the first impression. Okay. Yeah. But if you think about the 2D case we're dealing with, what does the 2D mean? This 2D means y equal to what? F of x, isn't it, right? So that's a 2D curve. Okay. How do you parameterize a 2D curve? So here's a 2D curve. How would you parameterize it from our previous lecture? One way to parameterize this thing is what? X equal to t and y equal to f of t, right? Or just maybe just replace this y of t. That's okay. So now if I parameterize the curve like this, so then we substitute this, okay, into this 2D formula here. If x equal to t, so let's see the s, what would s equal to? This dx over dt equal to x equal to t, right? So dx equal to dx over dt equal to what? 1. And then dy over dt, we don't know what it is, so we'll keep it as it is, right? So let's just keep it as it, so which is df over dt square, and then dt, right? So now if you look at, compare these two, are they the same, right? Yeah, they're the same thing, okay? Yeah. So basically, now from now on, you don't have to remember this formula now. You can just basically remember the general formula for arc lengths, either this one or this one, and that will naturally include this 2D scenario. Okay. Good. So let's take a look at a couple examples. Okay. So I think this should be very straightforward here. Straightforward basically means it's just simply to apply the formula to calculate arc lengths. Okay, here's a vector function, and we want to calculate the arc length as t goes from 0 to 2 pi. So before we jump into it, let's take a look at this one here. You actually You don't really have to calculate to know the answer. First of all, look at the r of t here. What kind of curve does r of t describe? Circle. Yeah. What's the radius of circle? Radius equal to 1, right? Yeah. Because the coefficient in front of cosine sine is 1. So, okay. And then we're going this t, right? Starting from 0. Basically started at where? We started at which location? Starting 0, starting from 1 and 0 location, right? And then it goes to t equal to pi. Okay? So imagine, basically, if you have a motion starting from here, it goes t from 0 here to t equal to pi. And where does it end? Where does it end as t equal to pi? 2 pi, so cosine 2 pi is 1, sine 2 pi is 0. So, but the question is, how does it go? It seems like it comes back to itself, isn't it, right? So, basically, it comes back to itself. Well, because this is 2t at here, even though this is pi, because this is 2t, right? So that basically tells you it goes 1 round after this 0 to pi time duration. Okay. Okay, so it seems pretty clear now. It starts here and it comes back to here. So what's the arc length? 0? It's the arc length should be what? Yeah, right? 2 pi r, and r equal to 1, so it should be 2 pi. Okay? Yeah. So now let's verify this, right? Let's see if I can verify this using the formulas that we just learned here. Okay? I'm going to use this formula. Okay, use this formula here. So which means I need to calculate dr over dt. Okay? So let's calculate dr over dt. So here's r. So calculating dr over dt 2, negative 2 sine 2t, and then cosine 2 cosine 2t. Okay, good. So that's dr over dt. And then I need to calculate the dot product between itself. Okay, so the dot product, so that'll give me 4 sine square 2t plus 4 cosine square 2t. So trigonometry is equal to 4. Okay, so finally your arc length formula is t goes from 0 to pi, and inside here is the dr over dt dot dr over dt times dt. So that basically is a 0 to 2 pi, 0 to pi square root of dr over dt dot dr over dt. So square root 4 times t dt. Okay. So that gave me 2 pi. Yes. Why this equal to 4? This you take out the 4 here. So sine 2t plus cosine 2t, right? This plus this is 1. Trigonometry. Yeah. Sine theta square plus cosine theta square equal to 1, right? Yeah. Sorry? Is it 2t you mean? Oh, it doesn't matter. It's the same thing, right? So I can always change as long as this is the same. 2t here, 2t here. So when you see sine theta square plus cosine theta square, that doesn't say what kind of theta it is, right? Theta could be 2t. Theta could be 3t. Could be anything, right? Yeah. Okay. Good. So that's the arc length, huh? Yeah, that's the arc length. There's another possibility that you could be asked for is, okay, saying, can you calculate the arc length as starting from here and then goes to an arbitrary time moment. Let's say maybe arbitrary here. Arbitrary meaning t equal to t, right? T equal to t. Then in this case, what you do is, all you need to do is replace that pi with a constant, with a variable time t, okay, with variable time t. But then you have to change slightly in terms of symbol at here, because we use a dt at here, isn't it, right? So maybe now we need to change this to, let's say, different domain variables. Let's say we call it tau, something like this. Okay, yeah. So everything else is the same. It's just the symbol wise, right? As a matter of fact, okay, nothing really changed. It's still going to be square root of 4, and then d tau. So all you get is a 2 times t. Okay, 2 times t now. So that will be basically a general function for the arc length. You plug in any time moment t, then you get the corresponding travel displacement, right? Yeah. Good. I do have another example. I think it's fairly straightforward. We're going to just probably skip that example there, okay? There's really the same thing. So the only thing I guess you just have to be careful is do it at this stage. Yes?
Just a quick question. When you integrated, you went from 0 to pi. Is there a reason you chose... okay. Is there a reason you didn't go from -1 to 1?
You mean the t's range?
Yeah.
Nope.
That's the t range, right?
Yeah,
Okay.
that's t's range.
Okay.
Yeah, not x range.
Okay.
Yeah.
Thank you.
Good. Yeah, so I'm not labeled the x number here. Basically, that's how t changes, or theta in this case, whatever you want to call that. Okay. Okay. The focus is actually on the next one, which is the with the Sclar line integral here. Okay. Sclar line integral. So I'm going to approach this Sclar line integral, not just presenting the formula, more or less to give you a different perspective to understand what exactly does this formula represent. Okay, yeah. So let's start from let's start from a very simple case. Okay, this is a very typical case that you probably see. Let's say I have a piece of wire from A to B. Okay, yeah. Now suppose that the wire has a density rho x. So then you probably will be asked is, what's the mass of the wire, right, for this piece segments at here. So we start from x equal to a and end up at x equal to b. I think 2d, right? That's 2d. And this is how we approached in let's say in 172. So we take a fairly small segment, okay, very small segment at here on the wire. So suppose this is at x of k location, okay, and this will basically can be represented using a small mass delta mk. So around that location x of k, a small segment of wire has a mass of delta m. Okay, delta m. How the delta m is calculated is basically you use the density at the location x of k, and then time the small segment of length delta x of k. Right, so that's your mass, delta mass. And then you can see, okay, for the wire mass, all we can do is we're gonna basically sum up all the small segments. If I have an n number of segments, then I'll sum all up, and that'll be the approximately, right? So basically, this is going to be the approximate total mass for the wire. Okay, so we substitute the rho term at here. Okay, substitute here. So that's your wire mass approximately by adding up the n number of segments. Then you get a total mass. Okay? But honestly, we don't want the approximate, we want the exact number. So then what do? So then we let this n go to infinite. So if there are the infinite number of segments, then we add the infinite number of segments together, and then you get precisely the total mass. Right? So when n goes to infinite, the summation sign, the finite summation sign, will become what? Integral. Okay, so it will become integral. So this time you're going to integrate from a to b for the x, and then this basically will become dx. Right. So that's how you calculate the density of a segment of wire, right, from a to b. Okay. Yeah. This is in 2D, right? This is in 2D at here. Now in 3D, right, we want the same thing. Okay. So let's do the same thing here. Let's see, we have a wire represented by a curve C. So here is curve C at here, and it starts from t equal to a and end up t equal to b, for example. Okay, so that's a parametric equation represented by r of t, or vector function r of t. So that's the wire. Okay, so basically you draw r of t is anywhere, right? That's your position vector. Let's see, we approach the same thing. Now we said, okay, we suppose, okay, we have a density. Let's call it rho x, y, z. Okay. Better yet, maybe let's say instead of using rho, well, that's okay. Let's keep it this way. That's fine. Okay. So we have a density rho x, y, z at here. So what does this mean, right? Basically means you plug in the coordinates at this location into this function x, y, z. Then you get a certain number, and that number represents the density at that location. Does that make sense, right? Yeah. So in 3D, I can't plot this out, right? It's a 3-variable function, 3 variables, so we can't plot it. But you can imagine, basically, as you're moving along the curve at each location, there's a number associated with that curve, right? And that number, in this case, you think of it as density. Okay? Yeah. And we want what will be the total mass, okay, for the wire between A and B at here. Okay? Yeah. So let's try very similar approach at here. Very similar approach. Now suppose I have a location at here representing its x of k, y of k, and z of k. So this is one location, okay? And we're gonna take out a segment at here, okay? And that segment has arc length of delta sk. So this is a small arc length, okay, around x of k, y of k, and z of k location. So the idea is, I want the total mass. Then the idea is, let's separate this total wire into n number of small segments. And each segment has an arc length of delta sk. Then we calculate the mass for one segment, then we add them up, right? And that will be approximately the total length, total mass for the arc length, okay, for this length of arc. So apparently your delta sk, okay, will equal to the density at x of k, y of k, z of k, time. Sorry, this is not delta. The small mass, okay, the small mass for that particular arc length equal to the density time the small arc length. Okay. Yeah. then the total mass is equal to the summation of all of the small mass segments that are here. Okay, yeah. So that's the total mass, and this should be approximate. Approximately, when you add them up, that's your total mass. Okay. So finally, you let this n go to infinite. Okay, let this n go to infinite, so that summation will become an integral. Then your total mass will become equal sign now. So in this case, we're integrating this function as your n go to infinite. So that segment arc length delta s will become smaller and smaller. Then this delta will become a straight d, right? So basically it will become a ds. Now integral, in this case here, we're integrating not just in terms of a t now, we're integrating, basically trying to integrate through this arc length, right? Through this arc, the curve at here. So I'll use a subscript here, the curve c, okay, representing basically the integration is along the curve c. Okay, along the curve C. Is that okay? Yeah. Now basically at the end over here, you see we end up with an expression. Okay, we end up with an expression for the idea of a total mass. That expression involves a scalar function, which is the density in this case, and this small arc length ds that here. And integration is along the curve C. So that's basically what we end up with. And this is what we call so-called scalar line integral. Okay, scalar line integral formula. It's a little bit awkward because it's not in scalar curve integral, it's called scalar line integral. Okay, even though you're actually really integrating is along a curve, not really along the line. Of course, curve includes the line, right? Yeah. So never mind the name. So that's basically the idea of a scalar line integral. Why this scalar? Because the function rho at here, this is a scalar function. That's why it's called scalar. In a later part of the lecture of the term, we're going to learn another type of integral which is called vector line integral. Okay? Yeah. It's still integrating along the same curve C, but we're going to integrate is a vector function now instead of a scalar function. Okay? So that's the difference. Now, I approach this with a very specific idea, which is to calculate the mass of a certain wire, right? But mathematical notation doesn't restrict itself to one type of application. So honestly, what you can write is, you should write very general here. So this is basically a general expression for any type of scalar line integral. Okay, so this is basically a general expression. Well, it's the same thing basically, except that forget about the density, forget about the physical meaning, right? Except that we're integrating this function over the curve C, and that will be it. Okay? Yeah. So all you can think of is in terms of mathematical concept is integrate f of x, y, z, okay, over this curve C. Okay, that's basically what it means. Good? Yeah. And I'll come back to explain this a little bit more in terms of another intuitive way of understanding this line integral later. Okay? But let's say for now, okay, what you need to understand is this is a scalar line integral, and the next is how do we evaluate this line integral? Okay? And that would be the next step here. To evaluate this vector line integral, it's actually fairly straightforward, because if I look at this formula here, what do I see? I see a scalar function. That has to be a function given. Okay, so the question will give you what this function is, and then all you need to figure out is what the ds is, right? And ds is actually what we actually just did, isn't it? ds representing the infinitesimal small quantity. This ds equal to over here. That's your ds. That's the small arc length. Okay. So this is where we can do the replacement in here. So because ds equal to equal to this, so this vector line integral. So here's what you need to do. I'll keep the bracket a little bit empty here for now. And I'm going to replace this ds with the formula we derived. That's your small segment of arc length along the curve C. So what do we do with the scalar function f? Function f is a function of x, y, z. So where is this location x, y, z? First of all, so you have let's say I have a space set here, right? And then you have f of x, y, z. Okay, so you plug one x, y, z into this function, you get the scalar value, isn't it, right? But now it's not an arbitrary location. The x, y, z is where? Exactly. It's on that curve C, right? It's on that curve C. So this x, y, z really should be the x of t, y of t, and z of t, which is a part of that vector function for the curve C. So because you're not integrating arbitrarily anywhere in the 3D space, you're integrating along the curve C, right? So that's where your x of t, y of t come here. So you need to replace the x, y, z with x of t, y, z of t. Okay? Once you replace everything here, then it's all about basically t now, right? Then we can look at what's the range of the t. Basically, where do you go from the integration from a to b, or from one moment to the last moment? So this integral limits here. So that basically will become the starting and the finishing time moment for the t. Okay, yeah. Now that's how you would actually make use of this formula here to evaluate the line integral. Okay, evaluate line integral. Okay, so let's look at a couple of examples. Okay, yeah. I'll give you a vector, scalar vector at here, a scalar function at here. Okay, and then we integrate. Okay, this guy over a curve C. So what's the curve C? So I'll draw it out at here. Okay. Here's the curve C. So it goes from origin to 1, 1, 1 through a straight line. Okay. Yeah. Okay. So this is a very typical question you will see during an exam. You're given a curve C. Not necessarily I'll give you the parametric equation for the curve C. And probably I'll just draw it out, right? But then you need to, in order to calculate this scalar line integral, you need to basically to obtain the parametric equation for this curve C. Okay. It's not going to be very sophisticated, right? Those are basically the one that I think that we've gone through some sort of a straight lines like this kind of here. It goes from 0 to 0, 0, 0 to 1, 1, 1. So what will be a possible parametric equation for this curve C? Can you give me one option here for the curve C? Somebody say t, 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 right? What's the range to the t? 0 to 1. Okay? Yeah. Now that's what you need to write down, not just the parametric equation, but also the range. because you need this as your integral limits at here, right? Okay. Okay, so now we continue here. Once we get this r of t, and we can calculate the derivative of this r of t, which is 1, 1, 1. And once we get this, and we look at the formula, here, right? The scalar function needs to be replaced, okay, the x, y, z needs to be replaced with x of t, y of t, z of t. So your f of y, z here can be replaced with x of t, y of t, and z of t. Basically means, what do? You replace x with t, replace y with t, replace z with t. So you look at this f of x, y, z here. So that's t minus 3t squared plus t. Okay, so that's your f of x of t, y of t, z of t. So putting things together now, right? Put together here. So this is your integral line, scalar line integral you're looking for. Here is your f of x, y, z. And then inside here is a dot product of the derivative r. So that's essentially what we're dotting here. We're dotting 1, 1, 1 dot itself, dt. Okay. And the t goes from 0 to 1. Okay, goes from 0 to 1. Good. So the rest of the things is a straightforward integral exercise now, right? From here, there's nothing new now. So 0 to 1, so this dot product, 1 plus 1 plus 1, 3, so root 3. So you can take the root 3 out of here, t minus 3t, so 2t minus 3t squared dt. So very simple integral. Okay. You will see that you end up with a 0. Okay, you end up with 0 here. In the past, you got a lot of questions. What does 0 mean? Right? So if this is a density here, then when you're integrating from this one end to the other, you get total mass for the y equal to 0, right? That doesn't make much sense. Well, maybe it does. So it's just here, it's just, first of all, if you forget about any physical meanings, it's just a mathematical calculation at the end. It's a 0, right? The integrals. Yeah, it's like when you're integrating a function, one single variable function. And then often in time, you also get a 0, right? Maybe ask you this. What does this 0 mean, actually? Can you give me an example? What does this 0 mean? K equal to... so when you're integrating a curve, right, like this, from A to B, okay? Area equal to 0, right? Which is okay. Negative plus positive equal to 0, okay? Yeah. Yes. Symmetric, yes. Yeah. So this is actually the point I want to make at here. What's the physical meaning of this? I give you a physical meaning, the mass, right? Single variable here give you, when you integrate a single variable from A to B, give you the total area underneath the curve. Okay? Yeah. So how about the line integrals, the scalar line integral? If I consider in 2D, okay, so back to the 2D, because in 3D here, you can't imagine anything at all. In 2D, so let me illustrate this here. So let's say I have a curve C. So this is the curve C, right? This is curve C here. Okay. So we are integrating through this curve C. And there's a function f of x, y. So 2D, right? So instead of f of x, y, z, it becomes f of x, y. Okay? So we're integrating this guy, okay, through this curve C. Does that make sense? Okay? So f of x, y, I can plot this. Okay, next lecture actually I'll be able to show you. Okay? When you have a function f of x, y. So let's say z equal to f of x, y, right? Okay, you plug in the x, y into this function, you got a number, isn't it, right? So that number can be the z component, okay? And this one here, if you plot it, in general, okay, you end up with a so-called, it's a surface, okay? It's a surface at here. Is that good? So this is your f of x, y. Okay. But in this case, we're integrating over the curve C. Basically, imagine there's a guy walking from one end to another end. Okay, so your f of x, y it's restricted, it's constrained to which value? To the x, y along the curve C, isn't it? Right? So the guide here will corresponding to a point on this surface, and the guide here corresponding to a point on this surface, and the guide here corresponding to the point on this surface. Is that good? Right? So as you're moving through the curve C, or as you're integrating through the curve C, so it's like there's another one traced out a curve on this surface right here. Does that make sense? Okay? Yeah. So basically, it's a very similar analogy to a scalar, to a 2D case now. As you're going from here to here, you have a function defined from A to B, and that's how the function looks like. And as you're going from here to here, you have a function defined, and that's how that function looks like. Okay? Yeah. Now, if I drop all of this here, if you imagine, okay, if you can imagine as you're going along, there's another one going along here. It's like you drop a curtain, okay? You drop a curtains from the top to the bottom here, okay? Yeah. So this integral, guess what does that give? So just like this, what does this integral give? Give you the total area, right? So on this integral here, what would it give? It will give you the total, same thing, the total area of this curtain set here. Okay? Is that okay? Yeah. If it helps you, actually, what you can imagine, okay, I can do this at here. Try to stretch the curve C to a straight line. Okay? Stretch it to a straight line. And then the corresponding top curve will also be stretched to a straight line, right? And then you end up with basically a rectangular, isn't it, right? Yeah, that's the area. It's the same area, okay? Yeah. Now, I can't extend this to the 3D variables. I can't do this to 3D variable, unfortunately. But for 2D, that's basically what it means. Is that okay? Yeah. So now you actually can feel, you can have two different ways to understand line integral. One is, I can think of this function f as a density. Or I can think of this, if it's a 2D, right? I can think of calculating the total area underneath that curve f of x, y here. Okay? Yeah, so either way is fine. Still have a couple minutes here, so let me just write down a property here, okay? Like a scalar function integral, okay, there is a very important property called additive property. Basically, if curve C is if curve C consists of n number of segments of curves, C1 to Cn, okay, then your line integral over the curve C can be separated into each one of them by adding each piece. Okay. That's basically the same idea as when you learn single scalar integral, which is called what? Piecewise integration, right? Okay, yeah. So that's additive. Okay. One example, we can't finish this today now. It's basically, if you recall that in previous lecture, just do this one in here. When we learned the vector function, the parametric equation, we basically did an example how to parameterize a curve C1 plus C2, this kind of situation. So here we want to do the same thing, but instead of okay, I'll give you this same vector function. Okay, we want to integrate the vector function through the C1 and the C2. Okay, yeah. So I'll talk about this in the next lecture, but it's fairly straightforward now. You can try to do it yourself even. First step, get a parametric equation for C1, C2, which we did, right? Yeah, and then apply the formulas, and you can get the line integrals. Okay. Any questions? Again, a reminder: the quiz next week. Okay, so make sure you go to your tutorial section to do the quiz.